Thank you and welcome to our seminar series. And this is our fourth talk this semester. And as you know, we have a lineup of speakers. And if you want to know more about them, you can also look on our YouTube channel where we record and host many of the talks if the speakers are open for sharing. So you can look at also the past semesters as well. If you have an idea for a talk, if you would like to give a talk, recommend a speaker, let us know. If you're also interested in anything else, get in touch with us. And so yes, today I would like to introduce Meliha. So Meliha Honic is a researcher and she focuses on enabling a circular economy in the construction sector through BIM, material passports, and blockchain technology. She has her bachelor's and master's from TU Wien and a PhD from the Faculty of Civil Engineering at TU Wien, which is also great. And with a focus on BIM-based material passports, which I think we'll hear more about today. I'm very looking forward to this topic. And she recently joined the chair of circular engineering for architecture here at ETH Zurich and is a postdoctoral researcher. And so I think we'll hear more about your talk today on digital technologies for material passports of buildings. So with that, I hand it over to you.
Thank you.
Thank you, Meliha.
Thank you very much for the introduction. So I hope everybody can see me well also online. So if not, please just write in the chat. And I hope that the sound is also fine. So yeah, thank you for introducing me. So I'm here at ETH since 6 months. I received a postdoctoral fellowship, so that's why I'm here and how I came to ETH. To my talk today, I will talk about digital technologies for material passports, buildings. And the main thing that I want to start with is, so each of you has a passport to travel from one country to the other. But have you ever thought of a passport for buildings, which makes
Yeah. I'm not sure I am seeing the screen advance.
You mean this one?
Yeah.
What do you see? The preview slide or?
The previous slide of the entire slide deck.
That's...
I think you need to share the...
Yeah, I have to share the
power.
Must be this one. So now, what do you see?
Yes,
does it work?
See this screen.
Okay, then go start again. So each of you has a passport to travel the world. But have you ever thought of a passport for buildings, which make materials travel from one building to the other? I will start my presentation with the current situation in the construction industry. And after that, I will give an overview of the whole presentation. So the current situation in the construction industry is that buildings consume a lot of raw materials, and that we are also, like the construction industry, is also responsible for 40% of CO2 emissions. Therefore, a transition from a linear economy to a circular economy is urgently needed. The main problem here is that we have a lot of materials in existing buildings. However, we don't have the detailed information of what is embedded in these buildings. So for example, what is the material, what is the amount of each material, what is the quality, and where can we find these materials? So therefore, we had proposed a material passport. For example, for the Empire State Building, it would say that it consists of 57,000 tons of steel columns, of 6,500 windows, and that it is built in 1931. These are just a few things that a material passport can show. I will go now more into depth of what it can tell us. Shortly, an overview of the presentation. So I will start to explain how a material passport can be compared for new buildings. Then I will proceed with how this method can be applied on an existing building. And the third part of my presentation is how we can get information on the building stock. through different digital technologies. So back to the first part. Here I will explain how it is compiled, what a material passport is, and I will apply the material passport on one case study. So what is a material passport? It has been, from several parties, it has been explained as a passport that gives value to materials. It's very similar how we have defined it in our research. So we would say that it is a qualitative and quantitative documentation of the material composition of buildings. So it shows which materials exist, what amount of these materials exist in a building, where these materials are allocated in the building, the share of recyclable and reusable materials, as well as waste materials that this building would cause at the end of life cycle of a building. And what we added additionally is the LCA. So we also assess the environmental impact of materials. In particular, this is the global warming potential, so GWP, the acidification potential, AP, and the primary energy intensity, PEI. And in addition, further information is required. That's the separability of materials, because it makes a big difference if two materials are glued to each other. It would be difficult to separate them, so to really get two clean fractions. So if two materials are glued, there is a way in this method to also have this integrated and to lower the reuse rate of these materials. Now to the scope of the materials. So today, in the first part of my presentation, I will show the MPA, so the Material Passport A, and the Material Passport B. And the second and third part will be about the Material Passport D, which is an inventory. So at the end of life cycle stage of a building. Now back to the MPA, so the Material Passport A. It is being generated in the conceptual design stage of buildings. And it enables a rough analysis and optimization tool in early design stages. So here you can make variant studies. For example, you can make a building out of timber and out of concrete, and then compare these two variants. For the preliminary design stage, the MPB, it also enables an optimization of the selected variant, but still you can make some changes of the layers and also replace some materials. For example, you have an installation which causes a lot of CO2 emissions, let's say so, and then you can replace it and try the new variant. I will not go into MP3, so the Material Passport C. And the Material Passport D is documentation, so it serves as an inventory of existing buildings. I don't know if all of you are familiar with BIM. So this Material Passport has been created with Building Information Modeling, so shortly BIM. I will just explain very briefly what it is. So a BIM is not just a 3D representation of a building. It also consists of the information. So the I in the BIM stands for information. For example, if you have a window within a building, it can show like the thickness of the frame and the material of the frame, and also of the glazing, if it's like 2-layered, 3-layered, and so on. And exactly this information is needed for a Material Passport. So that's why we used BIM to compile the Material Passport. Now to the structure within BIM and how this Material Passport is being generated. We start with the element level, because that's the level on which you build a BIM model. So that's one object, for example, a wall. Each of this object has a globally unique identifier. So this is assigned to each element when you model in BIM. With this, you can find the specific element within the whole building. So you have the allocation. When you scale down to the material level, you come to one specific material where the properties to generate a Material Passport are assigned. So for example, you have the timber layer, and then you have the property 1, for example. This can be the thickness, it can be the CO2 emissions, it can be the reuse potential, and so on. If we scale up, we come to the component level. It would be each slab which has the same material layers. They are summed up to 1. So slab 01 consists of slab 01A, B, C, and D, for example. And if you scale up everything, so if you sum up everything, you have the results of the Material Passport for the whole building. So you have all slabs, all windows, all walls, everything you have in a building. Which data did we use to do that? So I'm from Vienna, from Austria. So we decided to use an Austrian database, not only because it's Austrian, also because it delivers consistent data on material passport information and on the LCA. Because for the LCA, we have, as I mentioned before, the global warming potential, acidification potential, primary energy intensity. And for the material passports data, we have assigned to each material, we have a grade, which gives them a percentage of recycling potential. So for example, if a material has a grade 1, this is usually timber, it can be reused or recycled to 75%, and 25% of this material would end up as waste. And by linking each material with these grades, you then can sum up on the whole building the percentage of reuse potential and waste. And what else did we use? We used building elements. So these are predefined elements that you can get from this database. These were used because the names of each materials were the same. So we had consistent data. If we started to get material passports data from a different database, we would have the issue with mapping. So you would need to map, for example, the recycling grade from one database to the LCA data from a different one, and that would just cause problems. So we decided to keep it simple. We just use this database because also, like that was my PhD thesis, it was more the focus on how we can compile it with BIM and less the method behind. And here I would like to explain how like the recycling potential, like the masses that will be reused or recycled can be calculated. Just shortly, you see it is one wall with the area of 1 square meters. It's for a concrete wall, basically. We obtain the density from IBO, so from the database I mentioned before. The volume we would obtain from the BIM model because you model it such that you can obtain the volume from there. And the recycling potential you map also from the IBO database. And this is how you would, for example, for this wall, get a reuse masses of 207 kilograms. However, in this method, the separability is not considered, like in the IBO method itself. That's something that we added. They just propose to, for example, when two materials are glued with each other, so this is now in German, sorry, but if you have bitumen with concrete next to each other, you would then downgrade the grade. So if it was 2, it goes down to 3. So now to the part how we have done this. So on the one side, we have the BIM model, which we model based on a modeling guide. So this was also created by us within the project, and based on the building elements that we have obtained from IBO. These building elements, material names and element names match those from the material passport and LCA data. So that's how you can map them. On the other side, we have the data management and assessment tool. This is actually a tool integrated in BIM, which enables a bidirectional synchronization. So whenever you create something in BIM or make a change, you can synchronize that, and in the database, it's being updated. So for example, you tried one variant, you need a thicker insulation, let's say so. If you change that in BIM, this is automatically being changed also here, and all the assessments are being updated. So also the material passport you directly get from this data management and assessment tool. By the way, the name is Building 1. If anyone is interested, just let me know. I'm not making any promotion, but yeah, I just didn't mention it here. Sorry. Now a bit more in depth how the modeling works. Sorry. Now this is back to the design stages. On top you see that's the conceptual design stage. So in this stage, usually we don't have the information yet on like exactly which materials we will use. So in this stage, the designers would be able to model a building with dummy materials, so they don't define the material. But then they can map in the data management and assessment tool like different variants and can calculate, for example, the recycling potential and the CO2 emissions and so on. So they can get the results. And then they decide which variant they would like to work with. So again, like on the BIM side, you don't have any properties except the area and the classification. So you would need to model a wall really as a wall, such that you can map the right element from the data management and assessment tool. But the material does not have to be defined. And also the thickness does not have to be correct. You can change that in the data management and assessment tool. For the material passport B, so for the preliminary design, you already model with the variant that you have chosen. And the information that is being transferred to the data management and assessment tool is the volume, the thickness, and the material name. So from the data management and assessment tool, you just get the material passport data that you need and the SCA data that you map. So here you can still make some changes of layers and of specific materials and thicknesses. Now I will explain how we have applied that on a case study. This was an office building. It was not built. We just had the design of this building. And we tried this method on this building. Actually, this was the second one. We tried it first on a timber building. This is a concrete building. And yeah, it consists of 3 floors. And the load-bearing element is reinforced concrete. On the left side, you can see the model for the material passport A. So we don't have any materials defined. And on the right side, we see the model for the material passport B, where we already have multi-layered elements and the materials. So one of the results is this. It shows the recycling potential of the whole building. I did not put every results here, just that you know, but you can ask me later if you have more questions. The design of this has been done like very similar to the energy certificate, just that people feel familiar with it and would like to work with it. And the recycling potential here of this building is about like 50%, and the grade is 2.5. So we have grades from 1 to 5, and 5 is very bad, 1 is very good. To the results, what can the material passport show as well is the total material composition. So here you see it has a lot of concrete because the load-bearing element is out of concrete. And we also have some sand and gravel and some other materials. And on the right side, you see also the waste and recyclable mass of each material here. So for concrete specifically, it's 50-50. For sand and gravel, you have a bit higher recycling potential. And here you can see like where you could make some optimizations. But here, in this case, it's like concrete takes so much of the masses, so it would only be the only thing that you can change would be changing the load-bearing element. Yeah, these were the results for part 1 of my presentation. Now I will continue with the second part, where we have applied the material passport on one existing building. I will show the digital technologies that we have used to acquire data on this building. And we also did like a manual acquisition and then compared like the costs and the time efforts of these technologies and like the state-of-the-art data acquisition. So this was a real building of TU Wien, which has been demolished after we've been there. So we could use destructive methods to really check all the materials within the building. So that was the good thing about it. So now this building doesn't exist anymore. We did the manual data acquisition in 2 ways. We did a normal, like a standardized pre-demolition audit, which has to be done for buildings, I think, which are bigger than 700 cubic meters, like a volume. At least in Austria, this is the law. And an urban mining assessment, which goes more in depth, like where we checked really almost each wall, each slab, and so on to get the materials, like to get the material information. We also used laser scanning for the geometry. So with the handheld scanner, we had like scanned the interior and the exterior and obtained the point cloud from this building. From the point cloud, we generated the BIM model on the one hand, like manually, just on top of the point cloud. It has been like BIM objects have been created. What we have also tried is to, by using scan-to-BIM algorithms to reconstruct, like to do the automated generation of an IFC. But you can see that it works. Yeah, it works, but it doesn't work perfectly. So if you go back, there are some parts missing. So this is still something that we should work on, but that's not the main focus here. What we found here is just, we could see it's not easy to do like the automated reconstruction of an IFC, and we would need more information to generate the material passport. So in this stage, it would not have been possible to create a material passport with this model. So we have decided to not use that. Here the workflow to generate the material passport. There are several S, sorry, there is an A, but I think you already know that it's a passport and not a sport. So we have the geometry acquisition that was done with laser scanning. We created the point cloud and then the BIM model with dummy materials or without materials. Then we also did the demolition acquisition, that's the pre-demolition audit, and an urban mining assessment, which is more detailed. From both of them, we obtained the list. So the pre-demolition audit looked more into the quality and into like if there are harmful materials that we should not reuse or recycle, like asbestos, for example. And the urban mining assessment went more into depth, like we checked each slab, each wall, as I said before. Then we brought these two lists together. So we had the material composition of each wall, slab, and so on with the quality, and integrated that afterwards in the BIM model. And from the BIM model, then we extracted the list of the materials and again mapped it with the IBO database, like with the information that we needed to generate the material passport. What else did we do, which is quite a new thing? The ground penetrating radar we applied to detect materials within walls and slabs. Actually, the ground penetrating radar is not a new thing. It is being used for archaeological investigations on site, but it has not been used before, like for material detection within buildings. On the left side, you see like this is still the use case that we have used for that. So this person is applying the GPR on a wall. They have really done this like 3 times for each wall and quite often also for the slabs. So we had a lot of data. On the right side, you can see that you can also apply that like outside. This was a different project. I will come to that later. And the outcome is on the one side, it's a radar image. And on the other side, this ground penetrating radar is sending electromagnetic waves, which penetrate through the wall. And depending on how high the energy is from the wave that comes back and the frequency, you can make some assumptions about the materials. So this device does not say, okay, this is concrete here, but you get some values which you can use to like generate a model. And then with this model, you would be able to predict materials. So we are still working on that. These were the first results that we had obtained. So what can be seen easily, you can really distinguish pretty well between different compositions. For example, on top, we have a gypsum border wall, the green one. We had different values for that one, totally different than for those here. And also for the gray one. So you could distinguish, you could say here are different materials than here, but it was still not possible to really say, okay, this is, for example, for sure concrete, this is for sure this. So that was the first case study where we applied this technology, and we are still working on that. So building a database of typical constructions of walls, slabs, and so on, such that you would be able to predict for other buildings if you just go with this device once, if you apply it once, to see what is behind. One more thing, so apart from the values that we get, so the energy and the frequency, also you have the visual picture, so you have the radar image. For this example, it is quite obvious what is behind, because like this is the wall here. We have the metal profiles, and in between we have the insulation. So this is a typical construction of a plasterboard wall. And on both sides, you have a gypsum plasterboard. Yeah, the tool is being applied from here and sends his waves like that. And what we see here at the metal profile, the wave can't penetrate through. So that's why it stays here. And for the insulation, it can go up till here. So that's why it looks like that. So visually, if you have worked with this before, you could really predict what is behind. At least you can see that there are metal profiles and something in between. And for people who work in construction, they can make these assumptions more easy. Yeah, so this was that part. And we also did the cost and the time efforts assessment. For the yellow ones are the state-of-the-art method. The blue ones are the high-tech methods that we have applied. In the yellow ones, we have the BIM model generated based on 2D plans, like on documentations. And the integration of the materials information was also done manually. And for the high-tech method, we have the laser scanning, we have the GPR, and like the integration was still also manual here. But what we see, it takes a lot of time to really build up this database, like to process data that we got from the GPR. So this is mainly caused by the GPR, the time and the cost efforts. Yeah, but since we have tried this technology for the first time, it was difficult like to deal with the data. We didn't know how to structure it and so on. So since we are still working on that, it looks better now. But still, it is quite an effort to work with that. Yeah, that was my second part. I'm coming to the third part of my presentation, and I need some water again. So after we've done the material passport for a new building and for one existing building, we wanted to try with all these technologies we have applied before, if we can predict the material composition of the whole city. So therefore, we had a research project on that where we visited 10 buildings and made a data acquisition on site and to generate a digital urban mining platform. So that was the final goal of this project. So we did on-site investigations of 10 buildings, of 10 residential buildings in Vienna. So on the left top, you see that's a building from around the 1900s in Vienna. So that's the Wilhelminian style. We also have that a bit in Zurich, but not too much. So the facade is always looking very beautiful. Then on the right side, we have a building from the post-war period. There, like the concrete and the materials used were very cheap. So there were no beautiful facades anymore. And the third one is from around 2000. These are just three buildings, but we had all in all, we had 10. And we could cover like 3 construction periods. This is the Wilhelminian style, the post-war style, and the buildings around 2000. One thing that we wanted to do is to create archetypes from these buildings that we have visited on site. But what we found that for buildings around 2000, it's difficult because there are no typical buildings from like the 2000s because everyone just builds very different. You have a lot of materials. So it's not easy to predict the whole buildings of the city from this period. That's why we focused more on the Wilhelminian style and also on the post-war style. And we used GIS, so the Geographic Information System, to generate a digital urban mining platform for the city of Vienna. I'm showing some pictures of the on-site investigations. So yeah, this is our colleague who did the manual data acquisition on site. On the right side, this is a different building. You can see like it was not always easy to approach each wall and slab because of the furniture. So there were a lot of things still in the buildings. Yeah, also on the right, really beautiful furniture, but unfortunately it has not been reused. Yeah, so these were just some examples of the buildings. How did we do the upscaling on city level? So with using material intensities for each building that we have visited. So there are already approaches that are working on that. For example, from Kleemann et al. He was also from TU Wien. He has assessed the material intensities also with on-site investigations. But he did not use like laser scanning technologies and also no BIM models. So ours is based on laser scanning technologies such that we have a really accurate geometry of the building. And also the reconstruction was done in BIM. And from BIM, we assessed the material intensities for each floor. So we divided it into the basement, all the upper floors, and the roof floors, because we expect that the materials within these three divisions are quite different. So for example, for the Wilhelminian style, usually you have in the basement, you usually have concrete, in the roof, you usually have timber, and in between, you usually have brick. So that's why we made this distinction into these three categories. And what we've done is, based on the buildings that we have investigated on site, we calculated the material intensities, which are provided in tons per cubic meter. And to be able to predict the building stock of the building materials of other buildings, you map the gross volumes that you obtain from GIS. So on the right side, this is a model from GIS, divided also into these three categories. And by linking the gross volumes times the material intensities, you obtain the masses for this building. Once again, if it was not so clear, on the left side, you see the information obtained from investigated buildings to create the archetype. From this, you get the material intensities. This can be tons per cubic meter or kilograms per cubic meters for this typology. So in this case, it was the Wilhelminian style. And on the right side, you see the GIS model, which we obtained from the city of Vienna. And from there, you can get the gross volumes. And how did we map this? So we really used only residential buildings and buildings from this specific construction period. So either Wilhelminian style or post-war. And then you map the material intensity per basement floor with the gross volume that you obtain from GIS from other buildings, with the gross volumes. You do that for each category, and in the end, you can sum up and predict the material masses of one specific building or in the city. And this has been integrated in the GIS-based platform, which partly looks like that. So this is the reconstruction of the city of Vienna. Also, creating this GIS model was not an easy task. So we had different data sources and different data sets, which had to be combined to reconstruct the whole city. So this is just one part of it. And that would be the proposal for the digital urban mining platform. So here you would be able to select one building, and behind, it's calculating then the materials of this specific building. For example, for that one, we had a lot of concrete, so beton is concrete. You can also see, what I mentioned before, you have Kleemann et al.'s approach and our approach in our project BIM Stocks. And we just wanted to see if our results are kind of similar or very different, or if we did a mistake. So it looks similar, but still it's a bit different, but that's what we had expected. So, but there is not a big difference between his approach and our approach. So we can say we worked on the right thing, but still we cannot say if the final results, if his results are better or ours. So we still would need to work on that. Yeah, so with this platform, you would be able to really get information before you go to the building. So you don't have to go and make on-site investigations. On the platform, you could select a building, which maybe will be disassembled in the next 2 or 3 years. You could see which materials exist there, and you could make a plan for a new building and reuse some parts or many parts of the building. Yeah, that was it for the digital urban mining platform, and also my previous work. Yeah, so what comes next? As you have seen, it's quite an effortful process to obtain information on existing buildings, and time, huge cost and time effort to connect the start of life of building with the end of life of building. And for that, I proposed to use blockchain technology. The material passport information is here for the design stage, but we don't know if this information, for example, the allocation of a specific material in the building, the name of the materials, the masses, densities, and so on, will be available in 100 years. And this is the point where a new building will be probably constructed. And by having this information, we could reuse materials of existing buildings. So therefore, there are two reasons for blockchain technology. One is it enables tracking and tracing of components and materials throughout the whole life cycle. So you could store this information such that others, stakeholders after 100 years could make use of this information. And also you could prevent trust issues because stakeholders don't want to share all of their information. And with blockchain, you could really facilitate trust and could only share this information that you would like to share, and that only those people who you would like to have access would have access to this material, to this information. Yeah, this was it to my future plans. I would like to conclude with the 3 parts of my presentation. So what we can say for the first part, so for the new buildings, the material passport is an important optimization tool where also BIM serves as valuable data source, since you have all this information in the BIM model, if you have modeled correctly. Digital technologies show great potential to acquire information on existing buildings. Still, it is an effortful process to really do that. And third, a digital urban mining platform would be an important step for reuse and to enable a circular economy in construction. But to really refine the archetypes that we have built, we would need more case studies. So we would need to acquire more information on existing buildings, such that we can say that our model is really working well. Yes, all of this work would not have been possible without my colleagues and all the partners that have been working on the research projects and also the funding parties. Yeah, I would like to thank all of them. And I would also like to thank all of you who came here and also online. Yeah, that was it. Thank you.